So do you have any questions before we start? Now, if you remember what we were doing on Monday, what we started doing was just kind of trying to find a representation of nature in terms of some symbols, and we were defining some ways to manipulate these symbols. And we said that, okay, let's just use this ket notation to describe the properties of my system. All the information about my system is already included in this object. Now, of course, we have to be able to extract this information also from this object. And we were looking at the Sturm-Gerlach experiments. So we said that, okay, so if we have a Sturm-Gerlach experiment in the Z direction, when we send silver atoms prepared in an oven, we saw that they were split into two parts. So one, we labeled one of them as plus, the other one as minus. So at least this setup told us that there's a property of my system that can take two different values. And these two different values, we call them plus and minus. Of course, not everything can take only such two different values or discrete values. For example, we would also like to be able to talk about position of my objects. And the position can take any value, so that will be an infinite number of possibilities, that we will need infinite number of states describing the position property of a system or the momentum property of the system. So we will be, in that case, we will be using what we call the Hilbert space. And in this Hilbert space, it's just like a model of the three-dimensional real space. In real space, we just multiply vectors by numbers. We just sum vectors with each other. We multiply vectors with each other, so-called the inner product or scalar product. We do the same thing in the Hilbert space also. So if you have a, let's say, a ket, this is our notation for the vectors in this Hilbert space. We can multiply it by a number. So where A, this time, there can be any complex number, not necessarily a real number. We can add different states. So there is such an object. Then we define what we call the ket. For any vector, we define for any ket, we define the bra. So this is the ket. This is the bra. So this bra, you can basically think of it as it's like a function. You give it a vector, it gives you a number. And this function is defined with the inner product. So this bra, let's denote it by beta, it's a function. So when I act this on a ket, it gives me a number. And this number we define as beta times alpha, the inner product. Now again, for the time being, these are just numbers. We are defining them. We are not driving them. So this is our definition and how we will show them. So this beta alpha bracket is a number. Now we will define its properties later on. And then we said that, okay, for every ket, we can define a bra. And in fact, for every bra, we can also define a ket. And this mapping, so you give me a bra, I give you a ket. You give me a ket, I give you a bra. So we define this mapping also. So since we will be mainly dealing with such superposition of kets or bras, so we can also define their dual. Well, sometimes we will show it with a star, sometimes it will be a dagger. So this is defined as, you just take the kets of everything in your expression. Now if you have kets, you just convert them into bras. Kind of the only thing that's not trivially expected is that instead of taking A and B, we take their complex conjugates also. Well, this is necessary because we want to have the inner product of any two vectors to be a positive real number. So it will be measuring the magnitude of a vector, so which is a real number. So that is why we take this complex conjugate. So that if you want to calculate the magnitude of, let's say, this vector, this is nothing but the square root of well, this complex number the complex notation also makes sense if you because I mean basically we are just treating these things as complex numbers. So the magnitude of a complex number is just you take that number, multiply it with its conjugate, take the square root. So that's what we will do over here. So this becomes A complex conjugate alpha plus B complex conjugate beta. Of course, this is the bra, not the cat. A alpha plus B beta. And if you just open up the parentheses, it just looks like ordinary multiplication. So it's A absolute value squared alpha alpha plus B absolute value squared beta beta plus A times B star beta alpha plus B times A star alpha beta. So this is just if you ever need the magnitude, the amplitude of such a vector, or which is the sum of two cats. So this is how you can calculate it. Now, of course, here you see these two things. Well, they look quite similar to each other. They both have the vector, the cats alpha and beta, and they are in fact related with each other. This number should be equal to, well, let's just write it in this form. It is beta times alpha complex conjugate. Well, if you take the complex conjugate of a product, that's basically the product of the complex conjugates. The only thing is I also had to change their order. So they behave, in most of our definitions, they will behave like ordinary numbers. But sometimes you have to pay attention to their order. Because if you change their order, it will mean different things. And whenever you take complex conjugation or Hermitian conjugation that we will define in a moment, you need to change their order so that it will still make sense. So this will be equal to alpha beta. So beta alpha. This beta alpha is now, we define it to be just a number. Because remember, this inner product, it takes some vectors, two vectors, and gives us a number. In this case, it will be a complex number. So we can talk about its complex conjugation. And the complex conjugate of this number should again be another number. And that new number is just obtained by exchanging the bra and the cat in the inner product. Now, if we hadn't changed the order, you see we had this alpha beta complex conjugate. They say this is not equal to alpha complex conjugate beta complex conjugate, because this thing on the right hand side is the cat alpha multiplied by the bra beta. So we have this object. And this object is not equal to beta alpha. Because this is a number, and we had seen that this is an operator. So what an operator does, it just takes a vector, gives us another vector. So it's, in a sense, it's also just a special kind of function. So you give it a vector, it gives you another vector by modifying that vector in a well-defined manner. So how do we calculate this new vector? Suppose we have this operator. Let's say It's an operator, this alpha beta. We act with this operator on the ket gamma, meaning that that's an operator. We give it the ket gamma. It should give us another vector, another ket in this case. So how do we calculate this ket for this particular operator? Well, remove the parentheses. So it will be kind of obvious what you will get. Because if you remove the parentheses, this just becomes alpha, beta, gamma. So you see, this is just a number. This is defined as the inner product. So we have this operator. We give that operator a vector, gamma. And in return, this operator gives us this vector in the direction of alpha. Well, let's see. We multiply alpha beta with the bra beta, with bra gamma. Remove the parentheses. Alpha, beta, gamma. Well, this symbol doesn't mean anything. So this just doesn't exist. Let's try that one. Alpha, beta, we multiply it with gamma. Remove the parentheses. Gamma, alpha, beta. So this makes sense. This is a well-defined quantity. So these operators can act both in the ket space or in the bra space. On the ket space, here, we are multiplying the kets from the left. On the bra space, we are multiplying it from the right. So this brings us another question, in fact. So you see, this is a particular operator. Let's look at an arbitrary operator. Let's call it x. We said that, okay, so we act on this x, acts on the kets. So we give it a vector, it gives us another vector. So let's say this is, let me call this the ket beta. Well, I can take the dual of both of sides, or the conjugate of both of sides. So the right-hand side just becomes beta. So what is this one? How is it related with alpha? Now, okay, so well, since beta, the ket beta we had defined in terms of the ket alpha, the bra beta we should be able to define it in terms of the bra alpha. So there should be some operator which, when acts on the bra alpha, gives me the bra beta. And that operator, we call it X dagger. This is called the Hermitian conjugate of X. So let's do an example of this. We already have one simple operator above. So we had this. Let X be equal to alpha beta. So this was an operator. Now let's try to calculate its conjugate. Now we had defined the conjugate as, let's say, we took X, we act on it with gamma. When we take the conjugate of this quantity, it should be equal to the bra gamma with X dagger multiplied from the right. So this is how the definition of X dagger. Now let's look at the left-hand side. What is the left-hand side? We know what X is. X is already alpha beta. When we act on the ket gamma, so this is just alpha beta gamma. Let me take the complex conjugate of this one. Well, we know how to take the complex conjugate of all of those terms. This beta gamma is just a number. Alpha is a ket, so its complex conjugate or the Hermitian conjugate will be a bra. So this will be equal to beta gamma conjugate times alpha, or gamma beta alpha. I'm just taking the complex conjugate of this number. Now I can insert parentheses anywhere I like because of the associativity property of these multiplications. So this is equal to gamma beta alpha. So this, by definition, this should be equal to gamma x dagger. Note that this should be true for every ket gamma, because gamma was just an arbitrary ket that I chose at the beginning. But if this is true for an arbitrary ket gamma, so I know what x dagger is. X dagger should be equal to beta gamma, beta alpha. X was equal to alpha beta. You see, our notation of complex conjugation also works here. I mean, we could have just straight away calculate x dagger in this case. You see, alpha beta complex conjugate would be equal to, just if you treat that thing as the product of ket and the bra, its complex conjugate will be the product of the complex conjugates of the ket and the bra in the reverse order. So this will be equal to beta conjugate alpha conjugate. This is equal to, the ket beta multiplied with the bra alpha. No, bra alpha. Just as we had proven before. Well, this is the formal derivation of x dagger. But this simplified version also works well. That's because we are basically trying to define a framework that is consistent with each other, within itself. And in fact, either through this procedure or through this procedure, you can calculate the Hermitian conjugates of any operators. But just keep in mind that this thing, x being an operator, just doesn't make sense. So we have legitimate products, legitimate ordering of products, and some nonsensical products. So you have to make sure that at every step in your calculation, the symbols that you write are correct, they are legitimate. They should have a meaning at every step. For example, this has a meaning. So it's an operator, which when act on an arbitrary ket gives me a ket in the direction of alpha, for example. This is a legitimate expression. It's just a number, it's a complex number. I can take its complex conjugate, etc. This is a meaningful expression. I have an operator x acting on a ket. This is meaningful. I have an operator x acting on a bra from the right. Now, probably next week we will be seeing that we can show these as matrices. So we will see that the kets, we can show them as a column matrix. The bras, they will become just a row matrix. The operators will be just the square matrices. So we will see then also that expressions like this one, this just doesn't make sense. Or expressions like this one doesn't make sense. And then we know our rule for taking the complex conjugate of these objects. Well, in these two expressions, yes. Strictly speaking, no. So this doesn't make sense. This doesn't make sense. But we will use that notation to mean something different. So for example, we will be talking about, let's say, these silver atoms. So we already know that in a Stern-Gerlach experiment, one goes up, the other, some of them go up, some of them go down. So those are two different properties of these silver atoms. So they have this plus or minus property. But they also have a position property. So we can talk about the alpha times the beta. So this alpha describes whether it is plus or minus. This beta might describe, for example, its position. It's the product of two kets, but these two kets refer to completely different things. They don't both refer to the plus or minus property of the silver atom. I will try to be formally correct, but quite often you will see notations like this one. This symbol is just omitted. It just looks like the product of two kets, but those two kets should be referring to completely different properties of my system. They cannot refer to the same property. If they refer to the same property, they don't make any sense. Again, that is a different property of the same system. So we can have two particles, two silver atoms. One can be up, one can be down. So that is legitimate. Let me put 1, and the other one can be minus 2. So this makes sense. Because we have a given system, that system has two independent quantities. The property of the first atom, the property of the second atom. Again, the kets are referred to independent things. In that case, we can talk about the products of kets. Sometimes we will use the notation plus minus. Sometimes we will use the notation just plus minus in the same ket. But basically, they just mean the same thing. One of them is plus, the other one is minus. Well, you see, position and plus and minus information are different properties that can influence each other. You see, for example, if you take your silver atoms, send it through a Stern-Gerlach experiment, the plus-minus property determines its position afterwards, whether it goes up or down. The position depends on its plus or minus property. So it's the time evolution of one of the kets will influence the time evolution of the other ket. That is possible. But nevertheless, those two properties are independent properties. Independent in the sense that they refer to different things. Their time evolution might influence each other. Well, we will come to that later on, next week. Now we will see that, for example, there can be incompatible observables. Like we already have one example. For example, the plus-minus property in the z direction and the plus-minus property in the x direction. They are not compatible with each other. That's what the experiment tells us. We cannot specify both of them. We can, a better word for independent would be compatible observables. We can determine the plus-minus property and the position property at the same time. That would make a more formal definition of which kets we can multiply. Like position and momentum, they seem to be independent of each other, but they are not compatible with each other. We cannot determine both of them at the same time. So we cannot multiply a position ket, the position of a single particle, the position ket of that particle, with the momentum ket of that particle. It just doesn't make sense. Of course, if we have two particles, we can multiply the position ket of one of them with the momentum ket of the other one, because the position and momentum of different particles are compatible with each other. We can determine them. But we cannot determine the position and momentum of a single particle at the same time. Now we defined the Hermitian property, and we had actually seen that x dagger is not equal to x. So they are different objects, different operators. But there are a class of operators that have their conjugate is equal to itself. This is what we call a Hermitian operator. Well, it's just the terminology we use to specify the operators whose Hermitian conjugate is equal to itself. Well, if you go back over here, x and x dagger would be equal to each other if alpha and beta are equal to each other. So that's an example of an Hermitian operator. So alpha is an Hermitian operator. Now, for us, the Hermitian operators will be important. They will be our fundamental objects because they have a nice property that their eigenvalues are real. So let's first define the eigenvalues and eigenvectors. Let's say we have an operator. What this operator does, I give it a vector, it gives me back another vector. It just changes it somehow. It might rotate it, for example, and gives me another vector. So if I acted on it act on the ket alpha with this operator x, at the end I will obtain another ket. And in general, this new ket, although it is obtained from the alpha with the action of x, it can be in a completely different direction with a completely different magnitude, etc. So for example, just take the rotations. If you rotate something around the z-axis, you give it this vector, it rotates it, and it becomes this vector and this vector. They are related, but kind of independent of each other. They are not just multiples of one another. But if you take this rotation example again, if I give it a vector in this direction, after rotation, it stays in that direction. It doesn't change its direction. So there are these, for any operator, there are these special vectors such that if you give your operator this vector, it gives you a vector which is the same vector multiplied with some number, let's say alpha. Let's also call it alpha. If this is satisfied, this is not true for every vector, but if this is satisfied, in that case alpha is called an eigenvalue, and the ket alpha is called an eigenvector. Its direction doesn't change. It just gets multiplied by some number. That number can be 0, can be positive, can be negative, but it's just some number. For example, we talked about this operator, alpha beta. It's a non-Hermitian operator. We know that whatever vector we give to it, at the end we obtain a vector in the direction of alpha. X gamma is equal to alpha beta, gamma, which is a vector in the direction of alpha. So x acting on alpha gives me alpha multiplied with beta alpha. So this vector alpha is an eigenvector of my operator x. This is a number. And I give the ket alpha to my operator. It gives me another vector, which is the same vector multiplied with a number. So that's how we define the eigenvalues and eigenvectors. But this time, this beta alpha in general will be a complex number. So the eigenvalue of this x operator will in general be complex. It won't be real. Well, we said that for a particular value of alpha and beta, x is an Hermitian operator. So if this is, let's say, for this special x, this is a Hermitian operator. And, well, x acting on this ket alpha is just alpha, alpha. This is my x acting on alpha. This is alpha, alpha, alpha. Well, this is a real number. So if x, for this special case, for this special Hermitian operator, at least one of its eigenvalues is real. This operator has other eigenvectors and eigenvalues. We didn't study them, but at least we know that this eigenvalue and this eigenvector is real. Now, let's consider a general Hermitian operator. Then we can determine its eigenvectors and eigenvalues. Let us call our eigenvectors A or A1, A2, A3, etc. We might have a finite number of them, an infinite number of them. It depends on the problem. Let's just give them numbers A, such that these are the eigenvectors that satisfy x acting on any one of them is its eigenvalue times AI. So these kets, to label them, I would like to give them some names. And I just give their names, I choose it as their eigenvalue. I mean, rather than just calling them Ali, Ahmet, Ayşe, Fatma, etc. So I just call them A1, A2, A3, etc. Now the first one, there will be certain properties. This one I will not prove. So any vector, any ket, alpha can be written as this is equal to lambda I AI. So if you have any ket, it can be written as a superposition of the eigenvalues of this Hermitian operator X. This is called completeness. Basically, what we are saying that the eigenkets of this operator, they form a basis for our Hilbert space. A basis that just like the x hat, y hat, z hat basis in the real space. Any vector that you can write in the real space, it can be written as a superposition of the unit vector in the x direction, the unit vector in the y direction, and the unit vector in the z direction. So x hat, y hat, z hat, these form a basis for the real space. And similarly, any vector in our Hilbert space can be written as a linear superposition of the eigenvectors of a Hermitian operator. Now, later on, these Hermitian operators will basically will correspond to our observables. So when we are talking about some observable quantity, like the position of an object, the angular momentum of an object, or the energy of an object, then there will be a Hermitian operator corresponding to that, because those observables are real. So they will correspond to the eigenvalues of our Hermitian operator. And for any possible value of energy, let's say, then there should be some corresponding state. So this basically tells me that any state I can write in terms of some superposition of the energy eigenstates. The AI are real. So this is the thing that would be interesting for us. They have real eigenvalues. Well, to prove them, let's look at AI conjugate. If AI is real, AI conjugate should be equal to AI. Yeah, in fact, let us prove two things at the same time. AI are real, AI, AJ, this is equal to 0 if AI is not equal to AJ. So if I take two eigenvectors that correspond to two different eigenvalues, in that case they are orthogonal. Now, what does an eigenvalue, what does it mean that AI has the eigenvalue, AI ket has the eigenvalue AI? So if I take the X operator, act with it on the ket AI, this will just give me AI times the ket AI. And similarly, X acting on AJ will be equal to AJ times AJ ket. Now let me take the complex conjugate of the second one. Now if I take the complex conjugate, it becomes the bra AJ multiplied with X dagger. This should be equal to the bra AJ multiplied with AJ complex conjugate. But you see, X is Hermitian. So X dagger operator is equal to X. So this is equal to X. Now let me multiply from the right by the ket AI. This is equal to AJ conjugate AJ AI. Well, since AJ conjugate is just a number, a complex number, it doesn't really matter where I write it. So this is one relation I have. Now let us look at this one, this relation, the first relation I had. Multiply both sides with the bra AJ from the left. That gives me another relation. That tells me that AJ X AI, this is equal to AI AJ AI. So this relation I obtained from here. This relation I obtained from here. Now I can just subtract these two relations. The left-hand sides are the same. On the right-hand side, I end up having aj star minus ai multiplied with aj ai, this should be equal to 0. So this is my general relation. Now I can use it to prove what I wanted to prove. So let's take the first case. Case 1. AI and AJ kits can be equal to each other. Basically, J is equal to I. So, well, this tells me that AI complex conjugate minus AI multiplied with AI, this is equal to 0. But this is the magnitude of my vector, which cannot be 0 unless my vector is 0. I'm not interested in 0 vectors. So this is non-zero. So if this relation is to hold, AI complex conjugate should be equal to AI. That is, AI is a real number. So I started with an eigenvectors and eigenvalues of a Hermitian operator. Now we know that the eigenvalues are all real. Now the case 2, AI is different from AJ. Now in case 1, I just consider, here, in this derivation, I just assumed AI and AJ are quite general. They can be equal, they can be different. I didn't really make any assumption whether they are on their equality or difference. Now I obtain this general relation. And from this general relation, I'm just specializing to certain cases to prove my claim. One is this one. If the two kets are the same, then I see that the eigenvalues corresponding to those eigenvectors should be real. Now I consider the case that these two kets, these two states, they correspond to different eigenvalues. Now, if they correspond to different eigenvalues, nevertheless, this relation over here should hold. And keep in mind that AJ is a real number, so its conjugate is itself. So AJ minus AI multiplied with this inner product, this should be 0. Well, since I'm taking two states that have different eigenvalues, this thing is non-zero. So this has to be 0. So in a sense, okay, Hermitian operators have these two nice properties, at least they are eigenvectors and eigenvalues. Their eigenvalues are real, and their eigenvectors are orthogonal to each other. Well, just like in real space, when we want to choose some basis, we choose the unit vectors in the x, y, and z direction. Those are 3 vectors that are orthogonal to each other. We don't have to choose an orthogonal basis, but choosing an orthogonal basis makes our life easier. Similarly, in our Hilbert space, we don't have to choose an orthogonal basis, but again, choosing an orthogonal basis would make our life easier, so it would be nice if we choose a basis formed by the eigenvectors of a Hermitian operator. Now, furthermore, if AI is an eigenvector, so is lambda times AI. Lambda being some complex number, non-zero complex number. So, in fact, eigenvectors basically choose some directions. So if you multiply a vector with a number, you obtain a vector in the same direction. It's just magnitude is different. So whenever we are talking about eigenvectors, we are actually talking about some direction, some special directions for our operator, so such that our operator, when it acts on every vector in our space, it doesn't change the direction of those directions. Like rotations around the z doesn't change the z direction. So how to see that is kind of trivial. Let's say how we can see whether a vector is an eigenvector. You just act on that vector with your operator. So we have this lambda times ai ket. This is a ket. I can act on it with my operator x. Well, lambda is just a number, so it doesn't really matter where I put it. So this is equal to lambda times x acting on ai. Now here I'm using one more property of my operators, that x is linear. Not all operators will be linear, but we will be interested in linear operators only. So for example, an operator, as I said, you give it a vector, it gives you another vector. So for example, I can define an operator which multiplies a vector with its magnitude. This is not a linear operator. But if I define a vector that multiplies an operator that multiplies a vector with a number, which is independent of my vector, that's a linear operator. So since the operators we will be interested in will be linear in general, this lambda I can just take it out. But this is nothing but, since ai is an eigenvector of x, this is ai multiplied by the ket ai. ai and lambda, they are just some complex numbers. So their order, I can easily change them. This is equal to ai times lambda ai. We have the associativity property of all these manipulations, of all these products, so I can put a parenthesis anywhere I like within the products. So x acting on this vector, on this ket lambda times ai, also gives me the same eigenvalue ai times lambda times ai. Well, this will be nice because this allows me, instead of using these eigenvectors ai, I can use these ones. I can just divide every eigenvector by its magnitude. Now this will be nice because these new vectors will have unit norm. You see, in real space, what we do, to choose a basis, we choose x hat, y hat, z hat. These are vectors with unit magnitude. We don't have to choose unit vectors. We can choose as our basis, for example, twice x hat, 3 times y hat, 1/2 z hat. They form a basis. But again, it will make our life more difficult. If we choose unit normed vectors, it makes our life easier. So that's why we choose a normalized basis. So what we had actually shown here is, if we have a Hermitian operator, and if we can identify its eigenvectors, all its eigenvectors, they form, we can choose at least an orthonormal basis, a basis whose vectors are orthogonal to each other and they are normalized to 1. So this will always be possible. Yes, any questions before you go?
Bir saçma söz söyleyeceğim ama sıfır hariç bütün sayılar o zaman Hermitian operator'da diyebilir miyiz? Sıfır hariç bütün sayılar Hermitian operator'da diyebilir miyiz?
Correct. Multiplying by a number is an operation. So you give, let's say, 5. 0 is also a Hermitian operator. It's highly degenerate. All the vectors are its eigenvectors, and the only eigenvalue it has is 0. 5 is also similar. If you I can define my operator as I just give it some vector, it multiplies it by 5. So that tells me that, well, 5 times a vector is a vector in the same direction, multiplied by a number. So all the vectors are its eigenvectors, and the eigenvalue is 5. Well, that brings us to something that we didn't discuss here, degeneracy. So here I didn't consider the case when I might have two different eigenvectors that have the same eigenvalue. So this argument over here doesn't work. Because if you have here, this argument is based on the fact, this proof is based on the fact that the eigenvalues has to be different. If two eigenvectors have the same eigenvalue, they don't need to be orthogonal. But for the time, we will postpone their discussion to later on. Okay, we can still claim that for a Hermitian operator, we can form an orthonormal basis made up of its eigenvalues.
Şimdi mesela 5 operatörün dediğiniz gibi ben o zaman onun eigenvektörini aldığım zaman tüm vektörleri almış oluyorum. Bunlar oluşturduğum basis o zaman benim Hilbert space'im oluyor.
Okay, you see, now we will discuss this degenerate case. Let's leave it to Monday. I mean, you probably, some of you have some other lectures, and let's discuss it on Monday. So let's see what will happen in that case. Not all vectors will be my basis, but I can still choose a basis made up of eigenvectors of my operator, and these eigenvectors, I can choose them to be orthogonal to each other. Now, before, if there is no degeneracy, there is no choice. My operator already dictates me which catch I should take. But if there is a degeneracy, then I have some choice in my basis vectors. I can choose you, I can ignore him, for example, if you both have the same eigenvalue, etc. That we will do. Have you heard of the Gram-Schmidt orthogonalization procedure? That is what we will do. Okay, so that I take as no more questions.